electronic spectroscopy aside, as I said, work on some molecules, lithium molecules. I'll also send you some assignments by today or tomorrow. Work on the assignments, and then we will take a look at them in class. And so that you get familiar with how to derive term space for molecules. It's quite important that you do it, and we will work the examples out in class. Okay. What I will do now is we will start off with nuclear magnetic resonance. And this is very different from what we have been doing so far. And you will see what is different about NMR compared with what you already have studied so far. This is basically has to do not with electrons. Everything that you did in electronic spectroscopy has to do with electrons. You are moving electrons from one orbital to another. You are moving electrons from one orbital completely away, which is the photoionization experiment. So you are actually tampering with electrons. When you came to looking at vibration spectroscopy, you are actually looking at the molecular framework and seeing what happens to that. In rotations, again you look at molecular framework in terms of rotations and figuring out what exactly is the dynamics of the rotation process. In the case of nuclear magnetic resonance, we are actually going to be looking at the nuclei per se and see what that's the spinning nuclei. The nuclei are spinning, just like the electrons are spinning. And what the spinning nuclei is actually teaching us, what it is telling us. It's actually telling us a huge story about the molecule itself. And that's what we're going to be trying to figure out in the nuclear magnetic resonance spectroscopy, which is also abbreviated as NMR, and we have two NMRs on campus. And if you go back and see, one of them is actually 400 megahertz, and the other one is 600 megahertz. And very soon, at least by today or certainly by the next class, you will start to understand what that 400 megahertz and what the 600 megahertz actually mean. It actually carries a huge information about its specification. You will learn that. And of course, you have machines running from today. I think the state of the art is about 1000 megahertz or 1 gigahertz. That's supposed to be a state of the art machine. Many years ago, of course, we were looking at 60 megahertz in the 60s and 70s. If anybody bought a 100 megahertz machine, we thought he was rich. He bought 100 megahertz. I remember college and I in Madras had 100 megahertz. We are all these faculty members in our department are running around saying, wow, I had 100 megahertz. Today, you can probably buy 100 megahertz for your house if you want. You won't even get it because they don't even make it anymore. And in fact, we're trying very hard to see whether we can get one of these very simple 60 megahertz machines for the teaching lab. So in 211, you can actually run an NMR experiment. That's something that's on the card. We are negotiating with people to sell us one, and that will come very soon. So, if you have missed out on this, you can still come back into another lab in some other context and still use that machine. Nuclear magnetic resonance is extremely powerful, because it can actually tell you a lot about the molecular structure. So the word nuclear has nothing to do with nuclear energy or something. It's got to do with the property of the nucleus. And there are stories told that people who were working on NMR and they wanted to go to the US for a conference and they applied for a visa, the visa got rejected. Simply because they saw the word nuclear, they said, oh, you must be working in nuclear energy, so you can't get a visa. I mean, coming from GAE, I know that. If you are working in the nuclear energy department, GAE, you will probably not get your visa from many countries. They think that there is something you're trying to go there and get out of it. So many people who work in NMR, run into this problem. Therefore, they always keep saying that we don't work on nuclear magnetic resonance, we work on magnetic resonance imaging. And that's also the reason why the medical tool, MRI, is called MRI. They didn't say it as NMRI. They didn't say it as nuclear magnetic resonance imaging. Because if they only said it as nuclear magnetic resonance imaging, nobody would want to go into it. Because, oh my God, there's nuclear energy, nuclear radiation in it, therefore I won't go. There is no nuclear radiation. If at all it's got radiation of much less energy than what you would use for an infrared spectrometer. It's got much less energy than what you would use for rotational spectroscopy. It's got radio frequency radiation. And make sure using all the time to listen to your FM radios, Same frequency in fact. 92.3 or 98.7, right? This is 100 megahertz. You can see it's actually the same frequency that you're using for your radio transmission that you use for NMR. So the name nuclear magnetic resonance is conventional, but very often nowadays you see people talking about MRI, just say magnetic resonance imaging. They mean the same thing, and they simply want to remove the stigma of the word nuclear, and that's the reason why that's such. Now let's see how this method really works. Let's take a proton, and that essentially means a hydrogen. Let's not worry about the electron. Let's remove the electron and basically have a bare proton. If I have a bare proton, a nucleus contains bare proton, which is basically the H plus ion. Now what does the proton do? The proton can actually spin, just like the electron spins. And what is the spin of a proton going to be? Plus half or minus half. And if it is plus half or minus half, everything else you know. If it is plus half, what does it mean? It means that there is an angular momentum associated with it, which is root of half plus half plus 1, half into half plus 1. And what are the orientations of this guy with respect to a field? Plus half, minus half in terms of H cross. If I had n equal to 1, it is root of 1 into 1 plus 1. And then it has to be with orientation such that it is plus 1, 0 or minus 1 or other factors. Now I am telling you this proton has a spin of half. And what does that mean? It simply means that the angular momentum associated with this spinning proton has a magnitude which is root of half into half plus 1. That's the length of that vector. And that vector will actually have an orientation such that it has a projection of plus H cross or minus H cross on a reference direction. So how many possible orientations does this have? Two orientations, got plus half and a minus half. So while the angular momentum is half, the ML values or the projections on a reference axis is plus half and minus half. We never paid attention to this. But what's the energy of plus half versus minus half? Are they the same or are they different? What is the energy of ML equals plus 1, 0 and minus 1 for a p orbit? P orbit has three orientations, right? ML equals plus 1, ML equals 0, ML equals minus 1. Are they all the same energy or different in energy? Degenerate, we know that. L equal to 1 has three degenerate sets of levels, which is ML equals 0, minus 1 and plus 1. A spinning proton has plus half and L equal to half. And what are the projections? Plus half and minus half. And just by the same token that you learned earlier for the p orbitals, these two states must be same energy. So it's not right, but you can sort of imagine. If you say that plus half is one way and minus half is the other way, all I'm saying is it doesn't matter which way it is, the energy is the same. And therefore, there's really nothing to choose from, whether it's going to be this way or this way. Two are essentially degenerate identical energies. So if you want to draw an energy level diagram for these plus half and minus half states, what would I do? That's all I'll do, because the two states are the same energy. So if I have a proton, a bare proton, there's got a proton inside, which is the nucleus, basically the hydrogen nucleus without the electron. Got a proton inside, spin half, two possible orientations for that spin, which is plus half or minus half with respect to a field. But as long as I don't apply the field, the plus half and the minus half are the same energy. They are degenerate. And I can't really tell one from the other. It's almost like saying if you didn't have gravity, you can't tell up from down. Right? Because you have gravity, you keep saying that is up and this is down. If there is no gravity around, then what's up and what's down? Nothing. If I have no field, what is plus half and what is minus half? I don't know. It's all the same. They're all the same energy. They are degenerate in the absence of a field. Now what do you do? I apply a magnetic field to it. And that's where the NMR experiment is very different from your other experiments. I apply a field, and when I say I'm going to apply a field, I will choose a direction in which the field is applied. And let's say I choose a direction, some direction. The moment I apply a field, what happens to these two states? They are no longer degenerate. Because in the spinning, and there's a handedness to the spinning, the field will remove that similarity. If there is no field, this is this. But if there is a field, suddenly you will find that one of them is good, the other one is more demanding in terms of energy. As long as you didn't have a field, it doesn't matter whether you want to go up or down. There is no demand on energy. But the moment you put a gravitational field, what happens? Going up is different from going down. So immediately you have removed the degeneracy of those two states simply by applying a field. Now what field is this? It could be a magnetic field, it could be an electric field, or what have you. In this case, we apply a magnetic field. And anytime you apply a magnetic field and do an experiment, you are actually doing a Zeeman experiment. So all I do is I have this proton with me and I'm spinning one way or the other, and I have no way to tell which way it is. But the moment I put a field out there, then there is a big difference between this handedness and this handedness, and therefore the two are no longer degenerate, and you will therefore find that in the absence of a field, the two states which are actually degenerate will now split. They will have two different energies. This is something that you have to do if you want to make a transition from plus half to minus half. There is no way you can make the transition over here, because the two states are the same. How do you make a transition between two states that have no energy difference between them? But the moment I put a magnetic field, what happens? The field splits. And once it splits, I can actually jump from one level to the other by giving it a certain amount of energy. What's the big difference between this experiment and the experiment that you're studying for the entire course, starting from August? In all other cases, the molecules presented you with two states of different energy. Rotational energy, J0, J1, J2, J4, J3 and all that, they were all there for you, of different energy. And all you had to do was supply the energy and make a jump from J0 to J1 or J1 to J2 and so on. Vibrational levels. Levels are already there, non-degenerate. V0, V1 have two different energy levels. And if you use energy spacing, you provide the right energy and you jump from one level to the other. You did not have to do any preconditioning of the molecule to do the experiment. But here what happens is, if I want to make a transition from this level to this level, the molecule doesn't come to me directly. I have to dress that molecule up in some ways. So I take the nuclei, apply a magnetic field, produce a two states, and then come in with energy to make a jump from here to here. If I don't apply the magnetic field, these two will collapse and give me an degenerate set of states, and there is no experiment after that. So the big difference between this experiment, the Zeeman experiment, and the experiment that you are studying so far, the rotation, vibration, the electronic or photoelectron, whatever it is, you basically were actually just supplying the energy. The molecules presented a set of non-degenerate levels for you to work with. In the case of spinning nuclei, they don't provide you with a non-degenerate set of levels. You have to first get the levels to be non-degenerate, split them, put a magnetic field, split them, and then jump from one level to another, and then you have spectroscopy. In other words, there is a certain dressing that you have to do with this molecule before you can actually make the transition. So when you go to the NMR room, there's always this big tag put out there, people with pacemakers and people with things that are magnetic, please don't go inside. So it's not so serious these days as it used to be earlier. The reason being that there is a strong magnetic field inside, because they have to put the magnetic field first before they can do their experiment. And the magnetic field, mind you, these machines can be quite large. They have the order of 8, 10, 12 Tesla or thereabout. Large magnetic fields. So you don't want to go in there with things that can actually be affected by magnetic fields. Because today these machines come with large magnetic fields, they also provide an excellent shielding, so the magnetic field lines don't penetrate. But just for your safety, it's always said that people with certain issues do not go into areas with very strong magnetic fields. The fields are quite strong simply because If you have a strong field, you actually split these. Now, intuitively, you know something. If I have no field, this is it. If I apply a field, what happens? It splits. And what do you think if I increase the field strength? So if I want to have a huge splitting, what should I do? Oh, apply a very strong field. And therefore, you will therefore find that magnetic NMR machines can have extremely large magnetic fields, 8, 10 threads as well and so on. So that the field, so the two levels are split quite significantly, and then you can do the experiment between these two states. So what you do is, you apply a field, you split these levels, and soon you will see, of course, or maybe not today, you will see there are equations that actually relate what the splitting must be in terms of the magnetic fields. Let me just put it up there to get the field. Forget these. This is the field. This is the magnetic field in the z direction. So this energy difference is actually proportional to the magnetic field. Stronger the magnetic field, greater is the splitting between those two levels. This is a fundamental constant. It's called the nuclear magneton, and has got a certain value of the order of about 10 to minus 27 joules per Tesla. None of these you need to remember, because it will all be given to you in that question paper if you require it. And in any case, you can bring that one sheet with all these numbers on it. So you don't have to remember it. What you should actually do is, if you work a lot of problems, these numbers will actually get internalized, and you don't have to worry. It's actually 5.05 to 10 to minus 27 joules per Tesla. It's a fundamental cost.